For our fourth, and I can't believe it already, final panel, we're going to tackle the question of clean energy technology frontiers. Technology has the great potential to minimize periodic fuel shortages, fluctuating costs, global warming, and airborne pollution. Clean energy technology breakthroughs are a tremendous hope for climate mitigation as well as economic growth. I was reading an Atlantic interview just this week. The editor interviewed Bill Gates. He and others, as you may know, are pushing for a substantially increased R&D funding from the US government for energy specifically, from a level of about $6 billion to something like $18 billion. This would be a tripling. He argues, I think, quite compellingly for that. But the question for this panel is, where are the important technology frontiers? There's no one better to lead this discussion than Karina Edmonds. Karina is the Executive Director for Corporate Partnerships at Caltech, where she got her master's and PhD, and she's a nationally recognized expert in the field of innovation, technology transfer, and commercialization. Karina, over to you and your panel.
Okay, thank you. Thank you for that kind introduction. I'm so excited. This is really a sign of a great conference, because I thought I was going to be speaking to an empty room being the last panel, and everyone's here, and thank you so much for being here. I also want to welcome our virtual audience, because this is being webcast. And again, give thanks to DOE and MIT for hosting, and Mighty for putting together this great conference. I know everyone that I met today, I'm incredibly impressed with their backgrounds. And you've all seen the panels that we've had thus far, and this panel will not disappoint. We have a stellar group of scientists that are doing great work. And what I'm really excited about is that they really represent a broad spectrum of that pipeline of taking discoveries from the lab or the university out to the marketplace. And so without further ado, I'll start to introduce our distinguished panel. Furthest to my right, we have Dr. Nancy Haegel, who comes from the National Renewable Energy Lab, and she's a director for their Material Sciences Center there. And she will discuss her research in a minute, but I can tell you it has to do with electronic materials. And before you get up, Nancy, I just want to just do a quick introduction of everybody. MIT professor Angie Belcher, who, if you guys remember, you were mentioned at the opening of this conference. Professor Paula Hammond talked about her partner in crime and the great work that you guys are doing. And so we have her here, so that's a treat. And Leslie Dewan, who is CEO and also, I believe, an MIT grad. Yep. And Dr. Dewan as well. And she's now a CEO of Transatomic Power. And so we're really excited to have them. And the way the panel discussion will work is each of the panelists will have about 10 minutes to present their work. And then I will have a couple of questions, but really, if the audience has questions, I really much prefer to move right on to you, and we can take a number of your questions as well. So please have those prepared as we conclude their remarks. So Nancy, if you'd like to come up.
Okay, I'm going to stand up. I was actually told Angie was first, so let's see whose slides come up.
So I apologize. Let's see. We were switching back and forth.
Maybe you can give my talk. And
that would be...
Okay. That'd be really cool to have you just present Angie's work.
So can we have the first set of slides, and then we'll decide who's talking? It's me. All right.
All right. Thank you.
So I am going to stand up. My mother always told me to stand up tall. I never knew why, and now I learn it's because they're more likely to get elected. And I lived in Pacific Grove and learned that if you're tall, you're less likely to be attacked by a mountain lion. So I'm going to talk about NREL work, not just mine. I don't know if you've seen the charge to the panel, but I highlighted a few words. We can't do all of this in 10 minutes. New materials, nanotechnology, new materials, nanotechnology. So I decided to focus there. These are 7 of 9 pictures from an article in Scientific American in 2013 titled 9 Materials That Will Change Manufacturing. And I highlighted 7 that I thought would have something to do with energy. So you'll see catalyst materials, thin film, deposition, thermoelectrics for cars, disposable materials for packaging, magnets that can collect electronics, fibers, new plastics. And the interesting question for me is, which of these 7, perhaps, or the 9, are really going to change manufacturing? And how do we decide? So I'm going to make the following comments. One is that we demand a lot from the word new. And I think maybe a word is new should be better, right? Could be more efficient, could be more cost effective, could be more sustainable. I also think it's important in technology and in everything else to not get caught in the world of either or. We know that as women, you don't want to get set up that way, but also in the way we think as scientists. So it's not nano or macro. And I think one of the really exciting things about the field is the range, the magnitudes over which we are asked to think. Whether it's power, from the individual kind of 20 watts or so for light bulbs, all the way to the terawatt challenge for photovoltaics in the world. So 12 orders of magnitude. This is going to mean understanding size scales from angstroms to macro, so 13 order of magnitude. And at the end, I'm going to suggest time scales from the femtosecond to centuries. We would like a PV panel to last for 50 years. So half a century, all right? So if you look at that scale, 24 orders of magnitude, almost incomprehensible, all right? And I have some pictures at the bottom there that show the range of thinking that we have to have, for example, in photovoltaics or solar generation. And last, I think we share a belief, whether from a policy or technology or financial side, that distributed generation and storage are really going to change how we think about energy and who owns it. And in that sense, materials do have a history of enabling technological change and the corresponding social change that goes with it. So that'll be my last point. I'm from NREL. I have to show this slide. This is the efficiency as a function of time of a wide range of PV technologies and over history back to the 70s. And it's interesting to look at these and to see the range of technologies and then ask, what do we use and why and where are we thinking? So the highest technologies now are up around 46%, right? These purple curves at the top. Amazing, okay? But we don't use those very much. We use them in space. We don't use them for terrestrial power. Why? Because they're very expensive. And the nanotechnologies, you see the red curves there at the bottom, those are some of the quantum dots and new technologies people have been working on a while. We don't use those a lot either. Why? Because their efficiencies just aren't hard enough, even though we justify excitement about very low cost, okay? So if we blow this up a little bit, and then I put a circle around very broadly, the most important commercial technologies, they're all kind of right in the middle, right? And that's not because we're averaging, it's because of this driver between cost and availability and performance, okay? And, I'm probably risking going back, but I'm going to go back one. So in that circle, you'll see silicon, you'll see some of the thin film technologies. I want you to notice the yellow curve that's going up rapidly. I'm going to come back to that one at the end, the yellow with the red circles. Okay? This sort of makes the point. All right? This shows PV production by technology as a function of time, going back to 2004. The blue and the gold there together are silicon. It is over 90%. Right, of the commercial use. We have our thin film capability, our first solar folks up there in green and CadTel. But there are a couple dominant technologies in the market. Why is that? Well, over time, production decreases cost. So this is a log scale. I'm going to ask you to pay attention to the scales, whether you have a strong technology bent or not. We're going to go back and forth between linear and log. Logarithmic scales here, module price, cumulative production. The more you make, the better you do, the faster you learn. This is data that just came out from Fraunhofer ESA in October 2015. So you have an advantage if you're in the market and you're learning and you're growing. That doesn't mean there aren't new things in the horizon. It just means that the bar is high. Okay? So let's talk just for a minute about nanostructured solar cells, nano in a lot of fields. These are some images of different kinds of proposed nanotechnologies. This is a group at NREL, Matt Beard and colleagues. This came out in nanotechnology just December of 2014. Another interesting graph, linear scales, again, module cost along the bottom, module power conversion on the y-axis. So we want to be in that upper corner, right? We want low cost and we want high conversion efficiencies. So in gray, they've kind of indicated where we are now. All right? And then some of the promise of nanotechnology, which could be lower cost and higher conversion. So the obvious question is, why aren't we there? We've been doing nanotechnology for quite a while, right? Richard Feynman with his famous, there's a lot of room at the bottom, okay? Well, they indicate some of the problems. I've circled it in red there. It's transport. You have to move charge. A solar cell collects photons, creates electrons in its traditional way, but then you have to move charge. So my area of interest And we got the video to work. That's good, against all odds. What I've done scientifically myself prior to my move to NREL, but we're continuing it now, is literally visualize the motion of charge. These are pictures of electrons moving in materials. And even in that upper corner there where the data looks so beautiful, that's not a simulation, that's real data, okay? We generate a lot of electrons in the middle of that picture and watch how they diffuse. And we do this with multiple kinds of microscopes, electron microscopes and near field microscopes at the same time. So if you look at how far they're moving, you'll see that it's hundreds of microns. And those are outstanding materials, expensive, and we use them in many different forms, but we can see. So if we're going to do that in new materials, we're going to have to demand either that kind of transport or new ways to transport. So you also see transport in a nanostructure. We make electrons at one end of that nanowire, and they transport down. And at the bottom, some pictures of how electrons move under an electric field. Okay? So let me then end with a hot new technology, something I think you'll see more of. That was the yellow curve, perovskites, right? Why is the solar community very excited about perovskites? It's an ABX3 structure. You see the crystal structure there. An interesting material where people started with quantum dots. The first picture shows a perovskite quantum dot on a structure. But we've moved rapidly to thin films. These are mixtures of organic and inorganic materials, what are called inorganic hybrids. And a lot of excitement in the community because the efficiencies from these have gone from less than 5% up to 20% in a 4-year period, almost unprecedented. Diffusion lengths, the ability to move electrons in these, have been reported to be in excess of 175 microns. That's a long distance in this business. A little bit controversial still, but very promising. And there don't appear to be defects. The electrons and holes seem to be able to move in these materials in a way that we don't fully understand, but it has to do with the nature of defects that are created. So this is a low-cost solution process material with the potential to rival current solar technology. What's the problem? Well, 4 years is a short time, but there is a problem, and that is that these materials so far are not highly stable in water. They decay rapidly, so rapidly that the NREL people are hesitant to report efficiencies because the materials change so quickly. And this just illustrates some very nice new work from University of Notre Dame, where they look at the stability. They're showing changes in how this material absorbs light. So clearly we have to understand that. They believe it forms a hydride. That's what you see in the nice picture. But they're also doing femtosecond spectroscopy, literally looking at how charge is absorbed, or how light is absorbed and makes charge in times as short as 10 to the minus 12 seconds. So just an interesting example where we are going to have to do the most basic science and understand the most fundamental performance in order to make a product that can be stable perhaps for 50 years. Okay? So that's the range of things we think about. I'll just end with, we're back to, I think, what is it's a logarithmic scale, loosely defined. You know, we label historical eras by materials, right? The Stone Age, the Bronze Age, the Iron Age, creation of steel production, the invention of the transistor, and I put us here, you know, we're that last line. The red indicates the deltas in time, all right? So from 3.5 million years of the Stone Age, 2000, 1700, you can sort of see the compression occurring. So while I'm not going to suggest that you're going to see completely new solar cell materials in the next 5 years, I am going to suggest that the future appears to come faster, and maybe it'll be the perovskite era next. I don't know. Thank you.
Great, thank you. Thank you, Nancy. Next, I don't know if I'm on. Am I on? Oh. Okay, thank you. So next I'd like to just introduce Professor Belcher. And her work in what she has done is pretty amazing in the directed evolution. She's using directed evolution to engineer organisms that are actually creating new materials. And please.
Thank you. Well, thank you so much for this invitation to be here. It's a real honor. I was asked to talk about nanoscience and materials, and so my slides, I think, will come on in a minute. But the last talk was absolutely fascinating. I did notice that the first time scale was on the order of millions of years, but I thought I would start billions of years. I'd start back 4.5 billion years ago to the beginning of Earth. It only took about 1 billion years to have life on Earth. And then after that, we had organisms in the ocean that were kind of soft and squishy. This is my geologic time scale over here. But it wasn't until 500 million years ago that organisms in the ocean started making hard materials like abalone shells. These are biocomposite materials that are 98% by mass calcium carbonate and 2% by mass protein, yet they're 3,000 times tougher than their geologic counterpart. Why is that? Well, there's two reasons. One is it had about 50 million years of evolution to get good at making this material, and the other is that these materials are made on the nanoscale. So if you take these and you fracture them and you look at them in an electron microscope, what you'll find is they have these beautiful tablets of calcium carbonate, which is basically chalk, that's controlled by proteins, and those proteins are encoded at the DNA level. And so what I've been interested in doing is giving genetic information to non-living structures. So when a male and female abalone get together, they pass on the genetic information that says, this is how to build a material. Here's the DNA sequence, go out and make your own. So they pass it on to their offspring, same with diatoms made out of glass, like silica. And so I've been interested in giving information to solar cells and batteries so that they have the ability to evolve, get better as a function of time, and to pass on their genetic information how to make a better material. And so what I work on is the interface between biology and nanoscale, and you've heard nano a lot, and people know that nano is great because nano is small. Without nano, I wouldn't have this cool Apple Watch. But something that's more interesting about nano is when you take a large bulk number of atoms and you start to whittle it around down till you have a small collection of atoms, the way those atoms feel relative to each other and relative to other nanoparticles differs. And so it starts to change their optical, magnetic, electronic properties, their strength properties. And so biology already works really well at the nanoscale. So I work on energy, healthcare, and the environment at the interface between nanoscience and materials. And the idea is if you can control how these atoms are placed, if you can control what's next to each other, what's on top of each other, you can control many things like solar cells, batteries, fuels, CO2 sequestration, storage, water purification, therapeutics. These are all areas that I work on. People say, Angie, why aren't you more focused? And I'm incredibly focused. I'm focused on using biology to make nanomaterials, where those nanomaterials can have increased kinds of functions. So I thought I'd just show you quickly, and I work a lot with industry, and I founded 2 companies, Cambrios Technology, an electronics company, and Soluria Technologies, a natural gas company. So basically, we do this by evolution. We take organisms that have never had the opportunity to make a battery or a solar cell in their life. We genetically engineer them. We use simple organisms like viruses, like bacteria, and like yeast, and we force them to work with anything we want on the periodic table. That's why I handed out the periodic tables. I have some more. It's the same one I gave President Obama when he visited my lab. I gave him a periodic table. It said, in case you're ever in a bind and need to calculate molecular weight, and he said, thank you, I'll look at it periodically. So I have some extra of those. But we do simple genetic engineering. We take 1 billion viruses or 1 billion yeast and force them to interact with a battery electrode and see if they can take their proteins that they normally use for other things, grab the precursor battery electrodes out of solution and start to build it and fabricate it. Once you're able to have it, it's a Darwinian process, a survival of the fittest process. Once you're able to have that, you have it encoded in its DNA, and you can make millions and millions of copies. And these are papers that we've published on this concept over the years. And so we work on batteries. We work on anything. We work on lithium-ion batteries, lithium-oxygen batteries, and we've used this to build really great batteries through genetic engineering. Now, when the organism makes this in the ocean, it doesn't use toxic materials. It doesn't use high temperature or high pressure, and it doesn't add toxic materials back into the environment. We think incredible manufacturing idea. So what if we can get biology to do the same thing? And so we've made batteries that are what are structural batteries to be included in unmanned vehicles. We make little batteries that are for little drones and ones that can be integrated into textiles. And then we've worked on lithium-oxygen battery for long-distance vehicle applications. Here's 2 star students of mine who genetically engineered viruses to pick up carbon nanotubes with 1 gene and 1 protein. And they gave it a 2nd gene to grow a cathode material and then wire itself to a current collector. And that was this battery that's right here. We've worked on lithium-oxygen batteries. So my students said, well, let's use viruses to build better catalysts for these. And we were able to do that. We've worked with, you met my good friend Paula Hammond. She and I have worked together on several different kinds of solar cells, including dye-sensitized solar cells, where we've engineered biology to pick up carbon nanotubes, place them in the right place, such that when you shine light, an electron is injected into titania, it hits our virus. Our virus is carrying a carbon nanotube, and it actually is able to transport that electron more efficiently to the current collector. And then we've worked on these perovskite-based solar cells, which we're also very excited about. One of the things that was mentioned is that they're not as stable. But another issue to me about perovskite solar cells is that the best efficiency ones, the ones that are heading to 20% efficiency, are made based on lead. And I'd rather have a solar cell that wasn't a lead-based material. And so in my group, as well as other groups around the world, we're looking at lead replacements using these materials. But also, some really great students of mine said, well, what if we take car batteries? As we transition to next generation batteries, which will be lithium-ion batteries or other types of batteries, we're not going to need lead-acid batteries anymore. Now, lead-acid batteries in this country are very good at being recycled and reused, again, as lead-acid batteries. They said, let's take that and let's take that lead and let's convert it directly into a solar cell. And so they did that. They went and they got old car batteries. They isolated the lead out of the old car batteries, and they converted them with 95 to 97% efficiency directly into solar cells. And they did some calculations that from a single car battery, they would be able to make these perovskite, these thin nanoscale leveled solar cells that would be able to let's see, I have it up there, 13 US residents in Cambridge from one disposed solar cell for 13 residents from one disposed used car battery. And so I say let's look for other things to replace lead, but if not, let's take things that are going to be going and being recycled or put into a place that can be dangerous, and let's recycle it directly into solar cells. We also had a process where we genetically engineered yeast, the same kind of yeast you use to make beer or bread, and we engineered them to take waste CO2 and build floor tiles. We worked with a major floor tile manufacturer in the country to make biogenerative floor tiles based on waste CO2. And one of the companies I founded is called Solaria Technologies. I'm the scientific founder of. We used combinatorial biology and combinatorial chemistry and rapid throughput screening to develop a process for going from methane from natural gas directly into ethylene. So this is a process people have been interested in for about 30 years, but it hasn't been able to be done in a way that is commercially viable. Normally what you do is you take a longer carbon and you chop it down into smaller pieces. And we said, well, doesn't it make more sense to go from one carbon and to make it to 2 carbons and then have a controlled process to go directly into gasoline or diesel or materials that would be plastics? And so using this technology, we developed a catalyst that has a 60% reduction in carbon footprint from methane to ethylene. And it's a process that was developed in Solaria Technologies. And it's methane into ethylene, and then ethylene into gasoline or diesel. And it's actually, this is our demonstration plant that opened in the spring of this year, and it's me standing in front of it. We're making a ton of ethylene a day using this technology. So it took us only about 3 or 4 years to develop these new catalysts and then take it to demonstration scale. Another company that I founded is called Cambrios Technology. It's also a company based on nanoscience. It's a company that makes transparent conductors for touchscreens. And so almost all the devices that you have right now, you were able to touch the screen and check your email. It's all based on touch. Right now, most of those materials are based on indium tin oxide. And indium is a rarer material, and it can be mined in places that are less desirable for trade reasons. And so we invented a indium tin oxide replacement based on silver nanowires. And we make this solution called Clearome, and we're in about 30 products right now that you can buy in local electronic stores. Here's some of the products that we're in right now. It's solution-based processed. It's basically the way biology would make it. There's no biology in this product, but we learned to make it by using viruses. And it's roll-to-roll process, and it's much more environmentally friendly. And just recently, in the last few weeks, we've announced the first products in solar using this technology. So we've used this solution-based silver processing for solar cells that are used for developing countries for recharging batteries, as well as ones that are integrated into buildings for solar windows. I think that's what I have. Yeah. So those are the kind of things that you can use, using biology or learning from biology.
That's great. Thank you, Angie. Thank you. Okay, thanks. Thank you, Angie. That was wonderful. And next we have Leslie. And again, she's the CEO, and I should have known that everyone here is representing the full spectrum. She was going to represent the commercial side, but Dr. Belcher can talk to that as well, so that's great. So yeah, and also I just want to say I'm so impressed because in the innovation world, one of the hardest areas to innovate is actually in the nuclear sector. And so what is really impressive about the work that Dr. Dewan is doing is that that is exactly what they're addressing with their new nuclear reactor that she's going to talk about. So with that, thank you
so much.
Yeah.
Thank you all so much for having me here. This is such a fun event to be a part of, and such a fun panel in particular. So to start, I became a nuclear engineer because I'm an environmentalist. I think that we need nuclear alongside solar and wind and hydro and better battery storage if we want to have any hope of combating the horrible environmental effects of fossil fuels, of coal in particular. And so my co-founder, Mark Massey, and I, we started Transatomic about 5 years ago. And one of the pieces that really inspired us, we said, all right, like if we want to get new nuclear reactors produced in this country at any sort of scale, we need to find a way to build up excitement about nuclear power, to sort of rebuild and tap into that latent excitement that used to exist in this country surrounding nuclear. So for my leap back in time, I'm not going to start millions of years ago or billions of years ago. I'm going to start about 60 years ago. So this is a picture of the Atoms for Peace truck that was put together by the U.S. Atomic Energy Commission. It would drive around the country to big cities and small towns, and it would tell people about nuclear power. It would tell people about this exciting new technology that had so much potential to do good things for them, and people were literally lined up at the door to get in and find out more. Another piece I love to include, so around the same time period in 1956, Walt Disney produced a book and accompanying animated feature called Our Friend the Atom, where he sought to demystify the science of nuclear technology, so showing that it is just ultimately a fancy way of boiling water, while still just capturing the inherent mystery and wonder that something so small could contain a power that's so very great. And this, so this campaign, Disney's campaign, alongside Eisenhower's Atoms for Peace, marked the start of this age of great optimism for nuclear technology that went through the 1950s and 1960s. And during that time period, a large number of innovative types of nuclear reactors were developed and prototyped and tested. All of this ended very abruptly in around 1979 when there was a partial meltdown at the 3 Mile Island nuclear facility. So this accident, coupled with rising concerns about nuclear waste, effectively put the brakes on the industry in many ways, and the recovery has been slow and painstaking to this day. And so my co-founder and I thought, all right, well, how do we address these issues head on? How do you address the perception of safety, the waste, the cost of nuclear? How do you make a new nuclear reactor that people can be extremely excited about going into the future? So we started by adapting one of the earlier types of nuclear reactor designs and making a new type of nuclear reactor that can run entirely on nuclear waste. And so there's actually a tremendous amount of energy that's in the world's stockpiles of used nuclear fuel. So to put some numbers on it, right now there's about 270,000 metric tons of used nuclear fuel that exists worldwide. And if you're able to capture its remaining energy In our reactors, for example, we can capture up to 96% of the leftover energy that's in that fuel, and that translates into enough electricity to power the entire world for about 72 years, even taking into account increasing electricity demand. So ultimately, we want to start viewing nuclear waste as a resource to be tapped, rather than a liability to be disposed of. So this was actually based on earlier work conducted at the Oak Ridge National Lab in Tennessee, again in the 1950s, 1960s, early 1970s. They came up with a design for what's called a molten salt reactor that was extremely safe. It basically couldn't melt down, even under the worst case accident scenarios. But the older design was bulky and had a low power density. It was quite expensive. And no one at that time really cared about the safety benefits because it was before there had been any significant nuclear accidents. It was before Chernobyl, before 3 Mile Island, well before Fukushima. So it was effectively left on the table in many respects. My co-founder and I we were able to adapt that earlier technology to make it much more compact, power dense, able to run on nuclear waste while keeping those same safety benefits. One of the really striking things that I mentioned before is that the conventional nuclear reactors, they're only able to use a very small amount of energy that's in their nuclear fuel. So conventional nuclear reactors, they use pellets of solid uranium oxide that's held together by a thin metal cladding in what's called a fuel assembly. The metal that holds it together has to be very thin so that it doesn't absorb too many neutrons and shut down the reaction. But this also means that that metal is very readily damaged because it's literally in the core of a nuclear reactor. And also the fuel assembly framework tends to trap other products that serve to shut down the reaction. So the solid fuel can only stay in a reactor for about 3 or 4 years total before you have to take it out. And the only problem with that is that it isn't nearly enough time to use up very much of its energy. So the conventional reactors can only consume about 3 or maybe 4% of the energy that they could conceivably get out of the uranium fuel. So in some respects, this is why the used nuclear fuel is potentially so dangerous, because it has so much energy left in it. It's such an energetic product. What we're able to do in our version of the molten salt reactor is take the spent fuel assemblies, strip off the metal cladding, and dissolve the uranium fuel pellets into a molten salt. So we have a liquid fuel form rather than a solid fuel form. Since it's in a liquid, you're able to continuously filter out the fission products that would otherwise shut down the reaction. And since it's a liquid and not a solid, it doesn't have any material structure to be damaged. So you can leave it in the reactor for essentially as long as it takes to consume almost all of its remaining energy and split down the longer-lived waste products. And so one of the great benefits of this is that while conventional reactor waste, the majority of it is radioactive for hundreds of thousands of years, the majority of the waste that comes out of our reactor, by contrast, is radioactive for only a few hundred years. And so only a few hundred years kind of seems like a weird thing to say, but it makes it a human timescale for the problem rather than a geological timescale. Let's skip. Yeah, so there were 2 main materials changes that we made. One to the moderator. The moderator slows neutrons down to the right energy level to make them more likely to induce fission in a material. And we also changed the fuel salt. So we use a type of fuel salt where you can dissolve in significantly more uranium. And we used a type of moderator that's much more effective, so you don't need nearly as much moderator. So those 2 things in concert make the system much more compact, power dense, about half the cost of conventional nuclear power according to some external estimates, and lets it run on either very low enriched fresh nuclear fuel or the residual material in the nuclear waste. And in the interests of time, I'm going to skip these, but very, very broadly. All right, so we're the big blue line on the graph. I'm actually not going to skip this. This is interesting.
I have a few more.
So because of the type of moderator and salt that we use, we have both more fast neutrons, we're the big blue line here, and more thermal neutrons than is possible in the earlier types of molten salt reactor systems. And this allows us to avoid the middle or epithermal region where a lot of neutrons are lost from the system because they're captured by other isotopes that effectively take them out of, they're captured by other isotopes that don't contribute to the nuclear reaction. So we avoid the epithermal region, which is good, and we have more fast neutrons for breaking down the long-lived components of the waste, and more thermal neutrons for bulk heat generation. And let's see. So here's one of the initial schematics of the design and an external view. One of the pieces I wanted to close with is, so this system, like the earlier molten salt reactors, it operates at atmospheric pressure. So that's another good safety benefit, because it means that you don't have any driving force that could potentially push radioactive material beyond the site boundary. But it also leads to some really interesting and cool civil engineering considerations, because it's at atmospheric pressure, so you don't need as much of a big, heavy containment dome, the 6-foot thick concrete and steel containment dome of a typical plant. Your cooling needs are different because it's a liquid fuel rather than a solid fuel, so you don't need the large stack. So there's an opportunity to be very flexible about what the plant looks like architecturally and from a civil engineering perspective. And so I think that gives us this tremendous opportunity to change not just the underlying technology of the reactor, but change the way they look, to change the way people can fundamentally interact with this technology, to literally change the way they view the technology. And just in closing, in the last 20 seconds, 30 seconds that I have, so there's a really large number of young nuclear engineers just entering the field in their 20s and 30s right now. And it just makes for a tremendously fun time, because there are now dozens of small nuclear startup companies in the US and Canada working on just tremendously innovative technology. And it's a really rich field, and it just makes it tremendously exciting for me. Thank you all so much.
Thank you to everyone. And I know even for those of us who may not be a fan of nuclear power, I think the way you presented and the work that you're doing makes it that much more acceptable. And with that, I think one of the there's a lot of barriers to adoption of new technologies, but I think, have you thought about some of the societal barriers and how those might be addressed? You started your slide presentation with the education that was needed back in the early 60s and 70s, and are you guys looking at that, or?
Yeah, I think that educational piece is something that's crucial. And I think that there's a lot of potential benefits for nuclear engineers to be really open about not just explaining what their work is, but explaining why they're doing it, what makes them excited about the future of the field, and what they personally see the benefits as being. And I think, I don't know, I just like the idea of having nuclear engineers interact more with the public and talk about their technology, talk about why they are doing it, what makes them excited about the future.
Okay, great, thank you. And then I have a question for Professor Belcher. I noticed that you guys were able to take your technology to scale in 3 years for the plant. And that's really impressive, and just wanted to know the things that helped you to move that typical, it takes a long time to get technologies from the lab to the marketplace typically. So I was really impressed to see that was just 3 to 4 years for you.
Well, thank you. So, so it took us 3 years to go from what the problem was, is how do you get from methane to ethylene, to develop new catalysts to do it at lab scale. And so, and this was based on years of work also in using biology to make nanostructured materials. And then that was transitioned into this startup company, Solaria Technology, where a lot of the innovation happened in terms of how do you scale it, and reactor design as well. And so it took longer than 30 years, but it actually is pretty short in terms of both material standards and industry standards on how to develop a new route for a process. And a couple different things is that one is the technology that was ultimately developed that I showed you that was a demonstration plant. That's not a worldwide production plant yet. A lot of thought was put into how do you integrate into existing infrastructure and technology. And I think that was actually kind of key. The same with Cambrio's technology as well. You want to develop a new kind of science or technology that has an interesting application, but if you have to reinvent the whole manufacturing process, it makes it much more difficult. So I think it was a lot of design, and then as everything, it's hiring really smart people. And I want to move into your field now. All this is so exciting, all these great young people thinking about new ways of solving problems. So it really is, the people that we brought on board.
So thanks for bringing that up, that was a demonstration project. So what do you think the timeline will be to go full scale?
Yeah, I don't actually. I don't have.
You're not going to be.
Well, no, it's not just that. So I'm the founder and a consultant, but I'm not involved in the next scale-up stage. So I'm not going to guarantee what the timelines are, but I am going to say that it is possible, and it is going to happen.
Great, thank you. And then I have a question for you, Nancy, and I'll open it up if you guys have some questions, if you can start thinking about those. It was no surprise that we saw the same word in both of your presentations there, those perovskites, and I'm probably mispronouncing it.
Perovskites.
Perovskites, and that's really exciting. And you talked about probably the advances that could be made in the solar panel. Are there other applications for this material that you see that could enhance our lives?
There are, and some of the papers I've referred to, often materials that absorb light well also emit light well. So there is a lot of work in the potential for light-emitting diodes, solid-state lighting. That's one that certainly comes to mind.
Okay, great. And then with that, are there other material developments that you see that will, again, continue to accelerate the curve of the timeline on your?
In solar?
Yes.
I think the nano people are going to keep working, and there's a lot of interesting ideas. There's a lot to be learned from nature, right? And so solar fuels is a community that keeps working. We've found that nature has not only a long period of time, right, but obviously this genetic kind of approach that allows it, in a sense, to do many experiments at the same time. And so we're taking that approach in materials science as well. Computational materials by design, combinatorial materials, where instead of looking one material at a time, now you look at literally tens, if not hundreds of thousands. And I think that's going to change the field as well.
That's great. Oh, thank you. Sure.
Because I think that there's an interesting point in the fact that if you look at that beautiful roadmap and the materials and the devices and the efficiencies for solar, I think that this was one material that wasn't on the roadmap. It was a material that was made. It was a material that was known, and it went from 3% to 20% in 4 years. And so maybe this is the solar material of the future, but it gives material scientists like me hope that there may be other things out there that can go from zero to something significant in a short period of time. And so it takes into the idea of combinatorial material search and computational to look for this next generation material. We haven't discovered everything out there that could have a big impact in energy.
That's great. That's a great
You're
point.
probably familiar with a recent administration initiative called the materials genome. So again, bringing these ideas together.
That's great. Thank you. Do we have any questions here from the audience? Again, so that's great. So again, just bringing back, I know there's a lot of startup activity going on here at MIT, and so just wanted to know, Professor Belcher, from your experience as a professor and a faculty, and I know that this is something that's very interesting to folks, how easy was it facilitating that process of taking your technology from the lab to the market?
Well, at MIT, it's a relatively easy place to do it. It's actually encouraged, and so MIT is very supportive and helpful in that process. And I've been very fortunate to have a lot of funding and backing to get these technologies started. I mean, it's never easy, but going from the academic to the startup company is a huge part of our culture. And it's a great place to do it here.
That's great. And I'd like to follow up with Leslie, since obviously you got this started out of MIT as well, or was this some work after your PhD?
No, my co-founder and I, we started the company in parallel with our PhDs when we were about midway through the degree program. And I completely agree that MIT really really facilitated it. We worked extensively with MIT's venture mentoring service in particular. And yeah, I think that honestly, it wouldn't have been possible for us to do this company if we had been anywhere other than MIT. It would have been significantly harder for us, especially because it's in the nuclear field, which is not well known for its startups, I guess.
Sure.
some additional barriers there. But yeah, like we were able to, talk with friends of ours who were in, say, computer science or electrical engineering or mechanical engineering, who were all forming their own companies. And after enough of those conversations, we thought, all right, well, this seems feasible in many ways. And MIT helped us significantly with road mapping, what it might look like.
Sure. And speaking of road mapping, where are you there in terms of maybe building a demonstration of the technology or taking it to scale?
So we've raised seed funding for the company so far. We're backed primarily by Peter Thiel's Founders Fund, who is the main backer of Elon Musk's SpaceX, one of their early backers. So we're extremely grateful to be working with them. They're a fantastic group, and they like longer time horizon projects that have the potential to make a huge positive impact on the world. So right now we're doing lab scale testing, experimental testing of some of the key materials and components on the design.
That's great. Thank you so much. Nancy, sorry, did I see a question? Somebody pointed me to a question. Thank you, Andalyn.
Thank you for the wonderful presentations. And this question's maybe for both Nancy and Professor Belcher here. It's about the perovskites. And you have a technology where you're taking the lead from lead batteries and putting in perovskites. And I wonder, what's the thought process that brought you to envisioning a technology that would do that? And have you thought about other areas where that has a potential, where you can recycle something from something and put it into something that is a renewable or cleaner option? And have you thought about life cycles and greenhouse gas emissions with those? That was a long-winded question, but maybe you can answer a few points.
So for us, we didn't invent the perovskite solar cell. We wish we did. And when we worked in dye-sensitized solar cells, which have some similarities before, I work with Professor Paula Hammond on that, and the perovskite solar cells came out, and we were really jealous because they were already solution-based processed. They were already made at room temperature. Everything that we thought biology was really great at could already do with this particular type of material. And so we looked at it and we said, how can biology help us solve a problem? Because that's what we always say. We say, is there a roadblock? Can biology solve that problem? And we looked at it and we couldn't find a solution, but we really wanted to be in this field because it was really hot. And we said, but biology does things in a very clean way. So let's think about making it the cleanest process possible. And then because we also are a battery lab, we thought about going from recycled batteries, collecting that material, and then going directly into the solar cell. So that was the process. Wow, these are hot material. How can we get in on this? And is there a different way that we can approach it? And so we haven't looked at with the it's a very demonstration level. We've used it. We've built solar cells. We haven't looked at the overall CO2 cycle or carbon cycle from that. But we do this all the time with other kinds of materials. And so we went from waste CO2 into building supplies. Again, in that case, we used biology. We engineered biology to help us with the process. But that's a major theme in our lab in general, is how can you reuse materials, get biology to reuse materials so that you can make the most environmentally friendly process possible.
And there's a lot of thinking going on now in the perovskite community in different ways. I mean, one is that the solution processing will be a low-waste process. And as was mentioned, there are people working to replace lead, but they have not yet achieved some of the same results. On the other hand, I think it's also going to be important to really step back and think. I mean, for example, all your computers and all the lights and a lot of the things we're using here contain gallium arsenide. Now, arsenic is not a nice material either. However, in that form, it's stable, it's encapsulated. Our friends at First Solar are very successful with cadmium telluride technology and recycle and reuse that. So I think there's a lot of work to be done at looking at the overall process yet. And of course, we have not yet settled on what the performance limits will be or even what the right material will be. So.
Sorry, did I have another question? No? Okay. So on that, besides this new material, are there other, I just want to open up to the panel and ask, what material developments are you seeing that hold the most promise for efficiency and low cost in the area of clean energy technologies? So I know that's a really broad question, but I really want to give you an opportunity to think about the things that you see coming up, whether it's your lab or a fellow faculty or researcher. And again, I open it up to everybody. Maybe Nancy, since you're the center director.
Well, so the Scientific American list, I think, kind of shows the range of materials. We want things to be lighter, right? So that saves energy if we don't have to move so much mass around. So you see a lot of work in material science in that area, composites, affecting everything from wind to transportation to, our battery friends are always working with new chemistries. I think that we have a couple exciting ones in our center that they're working on. The solar community, what else?
Great, thank you. And then also, sorry, before I let you guys answer, follow up, what kind of industrial collaborations do you have? As we heard yesterday when Professor Hammond opened up, she talked about the importance of, again, transferring these amazing scientific discoveries from the lab to the marketplace. And we can only do that through startups and industry collaboration. And so being center director, are you seeing interest from the industrial sector to come in and pick up on these new materials?
Certainly, and of course, NREL's history has always been one of in the applied space, right? We're an EERE lab. We do a lot of partnering with industry, and I should know the number of partners we have. Our business people can always say it. It's an impressive number, trust me. The other thing that I think we don't want to lose track of, again, are the people. A lot of graduate students, and particularly postdocs, come through NREL and places like that, and they go out and are often key players in a lot of startups and companies like that. So the educational role, I think, of the national labs is an important one to keep in mind. We're not educational institutions in the traditional sense, but in the ability of a place to come for a period of time and see that breadth of expertise.
And that's an excellent
very
point.
Unique opportunity.
Yeah. That's an excellent point, and I want to bring up, it has been quoted many times that the best form of technology transfer is actually that moving truck of a graduate student from school to their next job. And so we shouldn't say that we're limited just to startups and corporations, absolutely, human capital. So Angie, I'd like to just open it up to you as well.
So in my academic lab, we love working with industry because we love finding out what the we only want to do work that's important and work that can be transitioned into the world. And so we like to find out what the problems are and see if working together we can have any solutions. And so in all the different areas I work in, we have industrial partners. So I work with Shell, I work with E&I, the Italian energy company, I work with GSK in pharmaceutical, and I've worked a lot in the electronics industry. And it's great to have a collaboration, to know that there's people interested in what you're doing in the lab and that it could actually go in and become a product or have something that could have a positive impact on the world. And then in companies, of course, industrial partnerships are absolutely critical for adoptions. And so that's another thing. I'm pushing MIT, but we're in MIT right now. But we have just an amazing interaction with industry, from our labs and through MIT and with students. And it's great because they want to hire our students, right?
Sure.
So it's a good interaction.
Thanks. And so, Leslie, I know you're in the nuclear space, but even in that space, I'm sure there's new materials that you might be considering for future fuel cells.
Absolutely, yeah. And one of the pieces that I've been dying to bring up is that perovskites are actually really good for immobilizing nuclear waste, like some of the actinide components, but especially the shorter-lived fission product components, because one of the tricky things with nuclear waste is that the particular atoms decay and they turn into different atoms while throwing off alpha particles or beta particles or what have you. So it can be really tricky to immobilize it in, say, a ceramic waste form. But perovskites, because they have basically the big open space in the middle, they have a trap that can kind of change into different conformations. So actually, some of my thesis research involved looking at perovskites for nuclear waste storage. So I'm psyched about that. Yeah, and then in other materials, I'm particularly excited about different types of silicon carbide-based composites or silicon carbide, zirconium carbide-based composites that can allow nuclear reactors, like many different types of nuclear reactors, to operate at higher temperatures, so you can get higher overall plant efficiencies and reduced corrosion in a lot of different configurations.
That's great. This sounds like a really special material, and it's really exciting to hear about it because I hadn't heard of this new material before. So like I said, any other questions? This is our last panel. This is your last chance to ask questions here. So again, this material is a subject that's near and dear to my heart. It was my minor, and I did silicon carbide composites myself. And so, it's just really exciting. And I loved the chart that you have, because another favorite quote of mine is, and again, I'm terrible missing quotes, but it's basically the advances in society are based on the materials available to it. The comfort of any society is based on those materials that are available to it, and the importance of these new materials being developed. And so with that, I want to bring it back to Professor Belcher, because the work that you're doing, maybe you can talk about the other work that these engineered organisms are helping us, and what are the other areas besides energy that they are helping us move forward.
Oh, I couldn't have asked you to ask a question more dear to my heart. So I'm a material scientist, so everything to me is a material. And so whether you're developing a material for solar or batteries or for cancer, it's the same to me. Same with my friend Paula Hammond, because we work in the same areas. And so we engineered viruses at one point to pick up carbon nanotubes, and we use those carbon nanotubes in battery applications, and then we use what we learned from that to go to solar cells. And then I was asked to join the Cancer Institute here a couple of years ago, and I was like, oh, I don't really know anything about cancer, and it was very intimidating. But I said, I know about viruses, and I know about carbon nanotubes. And so we started genetically engineering viruses to bind to ovarian tumors. These are viruses that are non-toxic to humans. They're bacteriophages. They're bacteria eaters. You're eating them right now, actually. And so they bind to ovarian cancers and then carry with them a fluorescent carbon nanotube that fluoresces in a special region called second window near IR, which is a region that is above 1,000 nanometers, but it's transparent to blood and tissue. And so what that allows you to do is actually see deep into the body just using a laser and a special detector, an indium gallium arsenide detector. And so we use the same technology that we developed for solar cells and batteries for ovarian tumors. And right now we're in animal studies for finding tumors that are less than 1 millimeter in size, where the gold standard is 1 centimeter. And working with surgeons and physicians at MGH, Dr. Beer's group, we've been able to develop a new system for guided surgery to, in animals, help increase the outcome by 40% survivability using guided surgery with these carbon nanotubes and these viruses and the technology we built around it. And so it's just basically saying, what's the problem? Okay, there has to be materials answer to it because it's a material world, and developing those. So that's a kind of a example. We work in lots of other fields as well.
That's great. And those interdisciplinary activities are so important because, yes, we can transfer from one field to another. And so with that, you kind of brought up the need for diagnostic tools. And so Nancy, as Center Director, let's talk about you create these amazing materials, but then you have to characterize them. And so what are some of the tools, some of the new tools, because I've seen a lot of new tools since I was in the lab that I'm very impressed with. And so what are some of the new diagnostic tools that you have for characterization of new materials?
Yeah, so that's an exciting field for us. It's about half of my center are people who specialize in different kinds of characterization. And I guess I think of it in terms of increasing our ability to see, right? Although we work powerfully with the computational people, and those are other ways to see, but increasingly now we have the ability to see, as I showed you, electrons move. We have the ability to see beyond the diffraction limit. It used to be kind of a resolution limit. determined by the wavelength of light. There have been breakthroughs in those. The Nobel Prize a year or so ago was all about imaging techniques that see beyond that limit. We're learning to be more and more sensitive in the ways we look at things. So that's a part of my center then that draws us across the whole NREL campus. And I just kind of want to bring us back. I mean, for me, one of the exciting things about being at NREL, and I've only been there about a year and a half now, is the breadth. So the materials are important, the technology is important, but you do it within a context of analysis and global thinking about policy. And I think that's been one of the exciting things about the meeting is people from all different areas. Because as we've seen, even for deciding on a material, there are different parameters. There's performance, there's cost, there's manufacturing, there's stability, there's scalability. They all have to come together. And then in an area like clean energy, we put that together with other values, right? The common home, the fact that as human beings, we increasingly don't do things just because they're the least expensive. We make a lot of value choices. And so it's been really exciting to be with this group of people where all those parts come together.
That's great. And sorry, and I did remember the quote, so I have to correct myself. So it's the comfort level of any society is based on the materials available to the society. So, and so we appreciate your work that you're doing in discovering new materials and characterizing them. But Leslie, I'd like to go back to you, and you mentioned computational tools, and I imagine those must be important in your development of this new reactor. So, are you working? Do you have tools, computational tools, or folks that are working on the software side to model the reactor and the reactions?
Absolutely, and that's a question that's extremely near and dear to my heart as well, because the focus of my PhD research was computational nuclear materials, and so if you examine nuclear materials computationally or nuclear thermal hydraulics or the neutronics of the reactor core, for example, you're able to increase you're able to iterate so much more rapidly on your design if you're able to do a lot of your testing in a computational environment. If you're able to simulate aspects of a nuclear reactor, you can comparatively very, very rapidly focus in on a very optimized design, a really elegant design. And that's especially important in a field like nuclear, where it can be very, very time-consuming to build actual prototype facilities. As much as you're able to do it, it's extremely beneficial to be able to do it computationally as much as possible for your initial iterations of the design.
Great. And because we're here and we're in a room full of women, which again, I am very excited to be. As an engineer, you're usually one of bunch of guys. And so I like to and there's a lot of students here who are probably considering different career paths. And so I like to take it back to Nancy. I noticed that you were a faculty member at Notre Dame, and even UCLA out in the West. And then you moved from being a faculty member over to a national lab at NREL. And maybe you can share some of your career decisions and paths, how you got where you are.
Well, I've been a faculty member at a couple of different places. I started at UCLA, and then for family reasons, we moved to the East Coast. My mother was there, and we needed to be closer. And then I promised my husband we'd go back, so we went back to California to the Naval Postgraduate School. It let me teach at a large, state institution, at a primarily undergraduate institution. I taught for the Jesuits for 10 years, and then active duty military from 30 different countries. Some people say I moved every 10 years because that's when they want to make you chairman, chairwoman, and so you move. But I've always enjoyed doing something new. And so the National Lab is a new challenge. And I've also, I worked for the Catholic Church and the Navy, and so I'm used to being in male-dominated environments. That said, it's great to be here, but I also think it's very important, to wherever you are in the kind of long timeline of history. And I was fortunate a few years ago to have a Fulbright and spent most of it near the old city of Jerusalem. So if you want to kind of get your time scales adjusted, you should go spend time there. Wherever we are on this long arc of history, you just seize the moment and go, right? And that's sort of been my pattern. We're still talking about issues that I was hoping we'd be done with by 2015. When I kind of started in the 70s and 80s, the arc bends slowly, right? But it's an exciting time, and you get the life you get when you get it. And so that's kind of been my attitude.
That's great. Thank you. And Angie, I know you also went to school out west.
Yes, I went to school in
Santa Barbara.
California, in Santa Barbara, a very beautiful place, a fantastic place to go to school for lots of reasons. And I took my first faculty position at University of Texas, Austin. I grew up in Texas, and my husband and I started dating in 6th grade. But I moved away in 7th grade, and we didn't re-meet till I was finishing my PhD, and he was going to medical school at Austin, and so I applied for faculty there. One application, one job, I got it. Very lucky. And I was in a chemistry department there, and I really liked it. But I'd never been on the job market before, and so a lot of other schools started saying, wait, you've never been on the job market, you never applied here. And I was being recruited once I was in my 2nd year, which is another good way to do it. I didn't have to apply. And so MIT kept recruiting me, and I kept coming out and saying, no, we're going to stay in Texas. And my husband's like, we're not moving to Boston. And so finally the 3rd time, I signed on the dotted line, and I came home and I go, we're going to Boston. My husband goes, oh, it wasn't part of the plan. But then we moved out here. It's a good 2-body place to live. He's a physician, and I'm faculty here. And when the reason I came here is I said it's like Disneyland for scientists and engineers, that I went to visit here, and everywhere I went, whatever the person next door was working on something even more interesting than I was working on, I thought, oh wow, everything is just so interesting. I always say I came here for the faculty, but I stayed for the students, because we have the most incredible students. Well, you have great students there too, but we have just incredible students. And I love teaching. I teach at the undergraduate level, but I also like mentoring a lot. And this is a job that you can reinvent yourself almost every year, because there's enough problems to solve that you can always pick another problem to work on. And it's not every day is perfect, but most days are good.
Great, that's great. Thank you. And then Leslie, I know you're just 5 years out, but are you, I'm not sure, it's been exactly 5 years, but this is your first venture out of grad school. And so maybe giving some advice to those women that are in grad school now in terms of, graduating and how you make decisions moving forward.
Absolutely. I really love your description of MIT and the Boston area as being like Disneyland for scientists and engineers, because that really resonates with how I felt about it. So I arrived at MIT as a 17-year-old freshman and basically never left. So I did my undergrad here in nuclear engineering and mechanical engineering, worked at a robotics company, an MIT spin-off company for a few years, then came back to grad school, did my PhD here, and now my company is based right across the street, actually. If you look through those windows, if the curtains weren't closed, you'd be able to see our office from here. Yeah, in terms of advice for people just starting graduate school, just starting in the PhD program, I think one of the most important things is to find a thesis project that you're really passionate about, something that you're excited to work on it for 20 hours a day, because you probably will be doing that. And and also finding people to mentor you among the faculty, and also building close collaborations with other people in your grad school cohort. Like that's where some of the most interesting projects that I've worked on, like outside of my thesis, have come out of that. That's where my company came out of, from discussions with my grad school classmates and talking about how we wanted the future of our industry to look like.
That's great, thank you. We have a couple more minutes if any questions? Okay, so no questions.
There's a question right there.
There's, okay, sorry. Thank you guys, and you can help me out with seeing hands.
Hi, my name is Allison Greenlee. I just finished up my life sentence at MIT in the photovoltaic manufacturing department, or photovoltaic manufacturing lab in the mechanical engineering department. And I had a couple of questions, namely about the timescales involved with commercializing these technologies and bringing them to scale. And I was wondering if you guys could speak a little bit, whether it's about the solar technologies or about the nuclear, trying to ramp that up.
Absolutely.
I take the first. Sorry, Leslie.
Oh, sorry. So nuclear, once you move out of the computational simulations, the timeframes for building prototype facilities or commercialization are quite long. So even by the more aggressive estimates, it would be, say, approximately 4 years out until you'd be able to break ground on a prototype facility for most of the new reactor technologies that are being developed right now, transatomics included. And among all of those advanced reactor technologies, realistically, the earliest timescale, the shortest amount of time before having an operating commercial facility would be approximately 10 years, and that's for all of the technologies that are out there. So it's definitely long timelines, no matter what country you're looking at building one in.
Great.
For Cambria's technology, so it was about 10 years. I mean, it depends on what we say scale, but right now in our manufacturing facility, we can make enough transparent conductor for half of all transparent conductors in the world right now. And it took about I think a little less than 10 years to be pretty well integrated into products. And Siluria we'll see we're at demonstration scale now.
That's great. Thank you. We had one other question.
I'm from University of South Dakota, and I am majoring in chemistry, and my background is material science. So I have a question. For the perovskite materials, is humidity a critical factor? And if it is it going to change the geometry from tetrahedral
Humidity.
to octahedral?
Yes, humidity is a critical factor, and actually the study I showed, that's what the parameter that they controlled. So yes, critical factor, encapsulation will be important. And then I missed the second part of the question.
Is it going to affect the geometry? The geometry
of the structure.
Well, that paper is an interesting result. What they're finding is that it's forming a hydrate form right near the surface. So they don't actually believe that it's affecting the inner part of the film. Now, that's one study. There are a lot out there, but their suggestion is that, at least at the beginning, it is primarily a surface-related effect. Then as it proceeds, you can degrade the full structure. But I think there's a lot of debate in this area still. So.
Any other questions? Well, with that, I'd like to just invite the entire panel to just, do you have any closing comments or parting words you'd like to share with the group? And we can
Well, I'll just start by saying, you're all welcome at NREL. If you haven't been, I've never been any place where so many people came up to me and said, I love NREL. So we're glad that a number of you do. And you're more than welcome to visit us at any time and across a whole spectrum of activities. It's your national laboratory, so we'd be happy to host you.
That's great. Thanks.
I guess mine is for the younger scientists and engineers and people and energy in the audience, that it's a fantastic time to be in the field. It's a fantastic time to be a scientist and engineer, because no time has there been an opportunity for us to make as big of an impact. And so I thank everyone here for dedicating your life and work to something that has such a promise and such an importance for the planet, but particularly for mentoring also younger people, even the smallest ones, to get involved in science and engineering, to know that they're in control of the kind of destiny of the planet. And so I appreciate everyone being here and everyone's hard work and dedication.
Thanks. Leslie?
And I want to echo that sense of excitement and that sense of urgency. Now is such a crucial time for developing new approaches for carbon-free electricity, for a better distributed grid, and these are the most important problems to be working on right now. And so it's something that it's thrilling to me, and I feel very lucky that I'm able to be in this field at this time.
That's great. Well, thank you. If you can all help me in thanking our panelists.
And our moderator.
Good job. Thank you, guys.